Okay, let's start our presentation for ICCV 2005. Today, my topic is adapting foundational segmentation models with heterogeneous searching space. I'm from Shanghai Jiao Tong University, and my research partner is from CATL. As you know, foundational segmentation models can be applied to many different fields. However, for domains with limited label data and infrequent usage, fine-tuning these models often becomes time-consuming and effective. Instead of fine-tuning, we propose a domain adaptation strategy. In our approach, rather than adjusting the model itself, we augment the input images before they entering the segmentation model. To demonstrate the effectiveness of our strategy, we select datasets from various domains. From our feasibility studies, you can see that compared with the original images, the augmented images achieve better segmentation performance. To achieve this, we designed a searching space that selects appropriate augmentation methods for each domain. This searching space including 10 learning-based methods and 22 rule-based methods, together forming a heterogeneous searching space. Here are some examples of our learning-based methods, including normal surface estimation, age detection, and others. Based on this heterogeneous searching space, our overall paradigm is constructed using reinforcement learning and carefully designed training environment. Step 1, we define a multi-discrete action space to map the available methods into an augmentation policy, which is used to augment images. For example, we may combine normal surface estimation, illumination adjustment, and median blur in one policy. Step 2, we apply the augmentation policy to the original image to generate the augmented image. Step 3, we feed augmented images into the segmentation models without any fine-tuning to obtain predicted masking. Then we calculate the intersection over union between the predicted and ground truth masks. To avoid local minimum, we randomly selected 2 additional training images, applying the same strategy and average their IOUs as the reward. Fourth, we feed this reward into our agent, which is trained using the proximal policy optimization algorithm. The agent then predicts the next action and returns to step 1. During training, we record the augmentation policy with the highest reward and keep the top 20. After training, we use these top 20 policies on the validation set, and one achieves the highest IOU becomes our optimal augmentation policy. Step 5, we use the validation set images to perform a distillation process. Each original image and its augmentation version forms an image pair, which we can use to train a generative model such as pixel to pixel. This allows us to accelerate the augmentation process. Here are some distillation samples. The generated images in the middle achieve similar effects to the manually augmented one. From our 5-shot and 10-shot experiments, you can see that our method significantly outperforms fine-tuning in common and camouflage domains. However, in ultrasonic and industrial domains, the improvement is relatively limited. From qualitative analysis, we found that depth estimation works best for accumulated objects. Normal surface estimation performs well in medical domains, and rule-based methods are effective in industrial fields. We also demonstrate that the distillation process using generative models is much faster than step-by-step augmentation. Here are some ablation studies explaining why we designed our reward function in this way. Another ablation study divides our learning-based methods into mild and radical categories. The results show that both types contribute effectively to the overall performance. Finally, our last ablation study shows that using reinforcement learning leads to faster convergence and more stable performance than randomly selection. That's all for our presentation. Thank you for listening.